Did you know the derivative of the natural logarithm of x is simply 1 over x? This elegant result is one of the most important derivatives in all of calculus. In this video, we'll show you exactly how to arrive at this result using multiple methods. You'll discover why this derivative is so crucial for calculus and see its applications in real-world problems. By the end, you'll not only understand how to find this derivative, but also when and why to use it. So let's dive in and unveil the mystery behind this fundamental calculus result. The natural logarithm, written as ln of x, is one of the most important functions in mathematics. But what exactly is it, and why should we care about its derivative? The natural logarithm is the logarithm to the base e, where e is Euler's number, approximately equal to 2.71828. This special number appears everywhere in mathematics and science. The key insight is that ln of x is the inverse function of e to the power x. This means if y equals ln of x, then e to the power y equals x. They undo each other perfectly. Now let's look at the graph of ln of x to understand its key features. The natural logarithm has some very important properties that make it special. Here's the graph of y equals ln of x. Notice several key features. First, the domain is only positive x values. Ln of x is undefined for 0 and negative numbers. Second, the function passes through the point 1, 0, which means ln of 1 equals 0. This makes sense because e to the power 0 equals 1. Third, the function is always increasing. As x gets larger, ln of x gets larger too. And fourth, the curve is concave down, meaning it's getting less steep as x increases. But why is finding the derivative of ln of x so important? The natural logarithm appears everywhere in real-world applications. In physics, it appears in radioactive decay and population growth models. In economics, it's used for compound interest and elasticity calculations. In engineering, it's essential for signal processing and control systems. The derivative of ln of x gives us the rate of change, which tells us how quickly these processes are happening at any given moment. This is crucial for making predictions and optimizing systems. In the next sections, we'll explore exactly how to derive this beautiful result using multiple methods, starting with the fundamental limit definition. Understanding where this formula comes from will give you deep insight into the nature of logarithmic functions. Now we'll derive the derivative of natural log x using the most fundamental approach, the limit definition of a derivative. This method shows us exactly why the derivative equals 1 over x. We start with the limit definition of a derivative. For any function f of x, the derivative f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Now we apply this definition to our specific function, f of x equals natural log of x. We substitute this into our limit definition. Next, we use the logarithm property that natural log of a minus natural log of b equals natural log of a divided by b. This allows us to combine the logarithms in the numerator. We can simplify the fraction inside the logarithm. X plus h divided by x equals x divided by x plus h divided by x, which simplifies to 1 plus h over x. Now we make a clever substitution. Let u equal h over x. This means h equals u times x, and as h approaches 0, u also approaches 0. Applying this substitution, our limit becomes the limit as u approaches 0 of natural log of 1 plus u divided by u times x, which we can rewrite as 1 over x times the limit as u approaches 0 of natural log of 1 plus u divided by u. Here's where we use a fundamental limit from calculus. The limit as u approaches 0 of natural log of 1 plus u divided by u equals exactly 1. This is a standard limit that you should memorize. Therefore, our derivative becomes 1 over x times 1, which simplifies to just 1 over x. We have successfully proven that the derivative of natural log x equals 1 over x using first principles. This first principles approach shows us the fundamental reason why the derivative works out to be 1 over x. The key steps were using logarithm properties, making a smart substitution, and applying the standard limit for natural log. Now we'll explore a second method to find the derivative of natural logarithm using implicit differentiation. This approach leverages the inverse relationship between logarithmic and exponential functions. We begin with our original equation, y equals the natural logarithm of x. This is the function whose derivative we want to find. Since natural logarithm and exponential functions are inverses, we can rewrite y equals natural log of x as e to the power y equals x. This transformation is the key insight of this method. Now we differentiate both sides of the equation with respect to x. The left side requires the chain rule since y is a function of x. Applying the chain rule to the left side, the derivative of e to the y is e to the y times dy dx. The right side simply becomes 1 since the derivative of x with respect to x is 1. To isolate dy dx, we divide both sides by e to the y. This gives us dy dx equals 1 over e to the y. Now we substitute back. Since y equals natural log of x, we have e to the natural log of x, which simplifies to just x. Therefore, dy dx equals 1 over x. This method demonstrates several key mathematical concepts. It uses the inverse relationship between logarithmic and exponential functions, requires knowledge that the derivative of e to the x is e to the x, applies the chain rule for composite functions, and involves algebraic manipulation to isolate the derivative. The result is the same elegant formula. The derivative of natural log of x equals 1 over x. Now we'll apply what we've learned to solve a practical problem using the chain rule with natural logarithms. Here's our problem. Find the derivative of the natural logarithm of 3x squared plus 1. This is a perfect example of when we need the chain rule. The chain rule for the natural logarithm states that the derivative of ln of u equals 1 over u times the derivative of u with respect to x. First, we need to identify our inner function u. In this case, u equals 3x squared plus 1. Next, we find the derivative of u. The derivative of 3x squared plus 1 is 6x. Step 1. We apply the chain rule formula. The derivative equals 1 over the quantity 3x squared plus 1 times the derivative of 3x squared plus 1. Step 2. We calculate the derivative of the inner function. The derivative of 3x squared plus 1 is 6x. Step 3. We simplify to get our final answer. The derivative of the natural logarithm of 3x squared plus 1 equals 6x over 3x squared plus 1. The key to success with these problems is always identifying the inner function first, then finding its derivative. Remember the pattern. The derivative of ln of something equals 1 over that something times the derivative of that something. So our final answer is 6x over the quantity 3x squared plus 1. This demonstrates the power of the chain rule when working with composite functions involving natural logarithms. Now we'll tackle a more challenging example that demonstrates the true power of logarithmic differentiation. We'll find the derivative of y equals x to the power of x. Here's our function, y equals x to the power of x. This is a challenging function because the variable x appears in both the base and the exponent. Standard differentiation rules like the power rule or exponential rule don't directly apply here. The key insight is to use logarithmic differentiation. This technique is perfect when we have variables in both the base and exponent, or when dealing with products and quotients of complex functions. Step 1. We take the natural logarithm of both sides of the equation. This transforms our equation from y equals x to the x into ln of y equals ln of x to the x. Now we use the logarithm property that ln of a to the b equals b times ln of a. So ln of x to the x becomes x times ln of x. This is the key transformation that makes this problem solvable. Step 2. Now we differentiate both sides with respect to x. On the left side, we use the chain rule. The derivative of ln of y is 1 over y times dy dx. On the right side, we use the product rule to differentiate x times ln of x. Notice that x times 1 over x simplifies to 1, so the right side becomes ln of x plus 1. Step 3. We now have our equation, 1 over y times dy dx equals ln of x plus 1. We need to solve for dy dx. Step 4. To solve for dy dx, we multiply both sides by y. This gives us dy dx equals y times the quantity L of x plus 1. Step 5. Finally, we substitute back our original function. Since y equals x to the x, our final answer is dy dx equals x to the x times the quantity ln of x plus 1. This is our complete solution using logarithmic differentiation. Notice how this technique transformed an impossible-looking problem into a manageable one by using the properties of logarithms and implicit differentiation. The key insight here is that logarithmic differentiation is the perfect tool when dealing with functions where the variable appears in both the base and the exponent. It transforms complex exponential relationships into simpler algebraic ones that we can differentiate using standard rules. Now that we've learned how to find the derivative of natural logarithm, let's examine the three most common mistakes students make and how to avoid them. Mistake number one is ignoring the domain of the natural logarithm. Here's a common error. A student tries to differentiate ln of negative 2x and gets 1 over x. But this is wrong. The natural logarithm is only defined when its argument is positive. For ln of negative 2x to be defined, we need negative 2x to be greater than 0, which means x must be less than 0. The correct derivative is still 1 over x, but it's only valid when x is less than 0. Always check the domain first. Mistake number two is forgetting the chain rule. Here, a student tries to find the derivative of ln of x squared plus 1 and incorrectly gets 1 over x squared plus 1. The student forgot to multiply by the derivative of the inner function. Remember, when using the chain rule with ln of u, we get 1 over u times du dx. Here's the correct solution step by step. First, we apply the chain rule formula. Then we find the derivative of x squared plus 1, which is 2x. Finally, we get 2x over x squared plus 1. Mistake number three involves sign confusion. Students sometimes think that the derivative of ln of absolute value x is simply 1 over x for all x not equal to 0. This is incomplete. The correct approach is to consider positive and negative x separately. For x greater than 0, absolute value x equals x. For x less than 0, absolute value x equals negative x. And we need the chain rule. In both cases, we get 1 over x, so the result is correct, but the reasoning must be complete. Here are 4 key tips to avoid these common mistakes. First, always check the domain before differentiating. Second, carefully identify the inner function when applying the chain rule. Third, consider all cases when dealing with absolute values. And fourth, always double-check your algebra. By keeping these tips in mind and practicing regularly, you'll master the derivative of natural logarithm and avoid these common pitfalls. Remember, mathematics is about precision and careful reasoning. Now that we've explored the derivative of the natural logarithm from multiple angles, it's time to consolidate everything we've learned and see how this powerful concept applies to real-world situations. The fundamental result we've established is that the derivative of the natural logarithm of x equals 1 over x. This elegant relationship is the foundation for many advanced calculus techniques. We explored 2 powerful methods for deriving this result. The limit definition approach shows us the fundamental meaning of the derivative, while implicit differentiation provides an elegant algebraic pathway to the same conclusion. We also mastered essential techniques like the chain rule for composite functions and logarithmic differentiation for complex expressions that would be difficult to differentiate directly. But mathematics truly comes alive when we see how these concepts apply to real-world situations. The derivative of the natural logarithm appears in many important fields. In population biology, when we have exponential growth described by p of t equals p naught times e to the rt, taking the derivative of the natural log of the population gives us the growth rate r directly. This means the derivative of ln p of t equals the relative growth rate, which is incredibly useful for analyzing how populations change over time. In economics, elasticity measures how responsive demand is to price changes. The formula involves derivatives of natural logarithms, where epsilon equals dlnq over dlnp. Using our knowledge of ln derivatives, this simplifies to p over q times dq over dp, giving economists a powerful tool for market analysis. These applications show why mastering the derivative of the natural logarithm is so important. It appears everywhere in science, economics, and engineering. To truly master this concept, I encourage you to practice with more examples. Work through problems involving chain rule applications and logarithmic differentiation until these techniques become second nature. There are many related topics that build on what we've learned today. Consider exploring exponential functions and their derivatives, integration techniques with logarithms, and advanced applications in differential equations. If this video helped you understand the derivative of the natural logarithm, please give it a like and subscribe for more calculus content. Leave a comment if you have questions or suggestions for future topics. Keep practicing, and remember, mathematics is a journey of discovery.